Okay, as promised, this is the continuation of section 14.4 where we get into the discussion of directional derivatives. All right, and so when we're talking about directional derivatives, we're talking about what is the rate of change in a function, typically of two variables, as we move in a prescribed direction. All right, so the handout that I've got here is a file that you can find on Canvas. I guess I should have told you to print this out and have it ready so you could take notes along with me. But this is the graph of, or the contour diagram of xy minus y squared, a function that we've worked with so far. So what we would like to be able to do in this particular problem is find a directional derivative, and the notation on this is f with a subscript of u, okay, and then at a point. So this means what is the derivative of this function, okay, in the direction of u, and I'm telling you that u is going to be in the direction of this vector 3, negative 1. All right, so on the picture, I've drawn a dotted line that points in the direction of this vector. And the first part of this is just try to approximate from the contour diagram the derivative at the point 1, 2 as I move in the direction of 3, negative 1. All right, so what I'm thinking is I'm going to start at this point and I'm going to move along this line. And I'm going to move along this line until I find a convenient point to stop. All right, and I picked this kind of on purpose. So I'm going to move along this line and I'm going to stop when I get there. Okay, and the only reason I'm stopping there is because that is a point that is on a contour, and it's also in the direction of 3, negative 1. All right, so what I want to think about then is how would I approximate that derivative? All right, well, the derivative, f in the direction of u, evaluated at 1 and 2, is going to be approximately equal to the change in the function divided by some kind of a displacement, we'll call it h. All right, so in the picture, the change in the function, well, we're going from a contour at negative 2 to a contour at 0. So if we go from negative 2 to 0, the change in the function is going to be an increase of 2. And then in the denominator, it was easier before when we were talking about derivatives with respect to x and derivatives with respect to y, because we were just moving horizontally or vertically. Now we're moving kind of at a diagonal from this point to this point. All right, so if you think about how far did we move, well, it's just going to be the length of that line segment. And we can find the length of that line segment by thinking about a distance formula or just looking at the hypotenuse of this right triangle. Okay. This side has a length that's equal to 0.25 according to the grid, and this side has a length that's equal to 0.75. Okay, so the denominator then would be the square root of 0.75 squared plus, this is actually going to be negative 0.25 squared, and we're going to get 2 divided by, and then when you simplify this on the calculator, that denominator ends up being about, well, it's the square root of 0.625, and you're going to get that this rate of change is, when I put this in the calculator, I get about 2.53. Okay, so 2.53 is an approximation for the derivative. And you should be thinking, well, this probably isn't a great approximation because this value of h is not really close to 0. All right, so what we'd like to do then is improve this approximation. All right, and so for part 2 on this one, it says use the difference quotient with h equals 0.1 to approximate this derivative. All right, so let me throw a clean copy of this up here. And what we'd like to be able to do is, instead of going all the way from this point to this point, what I really want to do is just move along a vector whose magnitude is 0.1. Right? That's what this means. We're going to move in a direction that's only 0.1 units long. Okay, so what we'd like to do then is find the change in the function from that point to that point. All right, so The difference quotient says to look at the change in the function divided by the displacement. All right, so the change in the function is going to be f evaluated at this endpoint minus f evaluated at the beginning point. All right, well, the beginning point is going to be the easy one. That's just the point 1, 2. All right, but now we've got to think about how much of a displacement is there here. All right, so this vector that we're going to be using, the displacement vector, is not 3, negative 1. This vector is going to be in that direction, but we want its magnitude to be equal to 0.1. All right, so this is one of those problems where here's a vector. I want a vector that points in the same direction, but whose magnitude is 0.1. So we said the process was to first make it a unit vector. So we would take the magnitude of this, which would be the square root of 9 and 1 is 10, and multiply it by the vector, 3, negative 1. Now it's a unit vector, but I want it to have a magnitude of 0.1. Right, so I'm just going to take this vector and I'm going to multiply it by 0.1. And so we're going to get a vector whose components are 0.1 over the square root of 10 times 3, right, or 0.3 over root 10. And the vertical component is going to be 0.1 over square root of 10 times negative 1. And I'm going to get negative 0.1 over the square root of 10. Okay? All right, so when I do that, I'm going to do this as a decimal first of all. This 0.3 divided by the square root of 10 is about 0.095. Okay, and 0.1 over the square root of 10 is about, I gotta find that one. 0.1 divided by the square root of 10. Okay, that's 0.0316 and negative. Okay, so this is a vector that points in the direction of 3, negative 1, but it's only 0.1 units long. All right, so we're going to get a better approximation for this instantaneous rate of change by using this one. All right, so we're going to take the value of the function at this endpoint, which is the x-coordinate is 1 plus 0.095, so it's 1.095. And then the y-coordinate is going to be 2 minus 0.0316, and that number is going to give me 1.968. All right, and then we're going to divide that by h, and h is 0.1. All right, so in order to get this approximation, I'm really going to have to rely on my calculator to do it. We're going to find that the numerator is negative 1.719 minus f of 1 and 2. I can get that either by plugging 1 and 2 into the function, or I can just look at the graph and say, I know that that's negative 2, and then divide that by 0.1. All right, so the numerator of this ends up being the numerator is 0.2806, and then divide that by 0.1, and you're going to get a decent approximation here of 2.806. All right, so if you compare those answers that we got, this approximation was 2.53. We got a new approximation of 2.806. And if I asked you which one of those you think is probably more accurate, I would hope you would look at this one and say, this one's more accurate because this displacement is a lot smaller than this displacement. And we'd end up getting a better approximation of an instantaneous rate of change over a shorter distance. Okay, now I think that you kind of anticipate we do a couple of approximations here, and then the next question is, what is the exact value? All right, and really number 3 on this one is really where I want to get to, is how do I find the exact value of this directional derivative? Okay, well, there's a way to do that, and that is to imagine that you're at a point, and let's say that this point has coordinates a, b. Right? And this is an ordered pair in the plane. Right? And then you get some value of a function. You get that this is an ordered pair that's going to be plugged into a function of two variables. And then what I want to look at is what is the derivative in a particular direction. All right, well, let's say that that particular direction is in the direction of this vector. And let's say that this is a unit vector. And we'll say that its components are u1 and u2. All right, and I want to find the rate of change as I move in this direction. All right, so I'm going to move in that direction a certain distance. And let's say that that distance is h. All right, so if I think about this as a displacement of h units in the direction of this unit vector, then I could say that this vector is really just h times a unit vector. It points in the same direction and its magnitude is equal to h. So if I think about this in terms of displacements, this displacement here would be h multiplied by u1. And this displacement would be h multiplied by u2. So the coordinates at this point here would be a plus this change in x, h u1, and b plus h u2. All right, so in looking at this directional derivative, f in the direction of u evaluated at AB is going to be a limit. It's the limit as h approaches 0. Right? We want this displacement to get really, really small. And it's the change in the function, f evaluated at this endpoint, a plus h u1 and b plus h u2 minus the value of the function just at AB, and then divide that by h. Okay, now at this point we look at that numerator and we're going to have to remember something here. All right, something that we talked about the other day, and that was the differential. And we said that the differential was df, and it was really the change in a function due to a small change in x and y. And we said that this differential was the derivative with respect to x at AB times a small change in x plus the derivative in the direction of y at AB times a small change in y. Right? So this is a recall that this is the case. Okay, so if you look at the numerator of this, this is the difference in the function from one point to another. So let's jump down here and say, well, this is the limit then as h goes to 0. And I'm going to replace the numerator with df. Okay, that's all that is the change in the function due to a small change in x and y. Right, and this is then the limit as h goes to 0, and I'm going to substitute this expression into the numerator. Right, so it is fx at AB. Right, and then if you think, what is this dx that we're talking about? The dx is the change in x from one point to the other, and that happens to be just h times u1. Right, so let's substitute in here h times u1 plus fy evaluated at a and b, and then the dy is just the change in y, which is h times u2, and then all that divided by h. So the nice thing about this is we get the limit then as h goes to 0. Right, and then if you notice, this is just multiplication in the numerator, and I've got a common factor in these two terms of h. So if I factor out the h, I'm going to be left with fx at AB times u1 plus fy at AB times u2, and all that divided by h. Now the really nice thing about this is those go away. And we're going to be left with this expression, which isn't really dependent upon h anymore. All right, so we get to this point where we can say then f in the direction of u, evaluated at AB, is equal to fx at AB times u1 plus fy at AB times u2. All right. The other thing I'm going to look at is this looks kind of like something we talked about with vectors. Okay, we got something times something, and then we got something times something. This looks a whole lot like a dot product. And this would be the dot product of fx at AB and fy at AB dotted with u1 and u2. This is kind of cool. This is what we talked about on Wednesday, was the gradient of f evaluated at AB. Okay, remember, that's a vector. And then this vector is just the unit vector in the direction we're trying to travel. Okay, so this is where I really want to end up, and this is the definition of the directional derivative. So if I want to find the derivative of some function at a given point in the direction of a unit vector, all I have to do is take the gradient at that point and dot it with a unit vector in the direction I want to travel. Okay, so back to our problem then. The problem asked us to find the exact value. Find the exact value of this. All right, so in order to do this, we want to say find the gradient of f. I want to evaluate that at the point 1, 2, and I want to dot it with a unit vector in the direction that I'm moving. All right, so I got to do two things here. I got to first of all find the gradient. All right, so the gradient is just the partial derivatives. There's the function. All right, so the gradient of f as a function of x and y is what we did the other day. This is the derivative of this with respect to x is y, and the derivative of this with respect to x is y minus, sorry, not y, x minus 2y. All right, so I want to find the gradient at 1, 2, so I'm going to plug 1 and 2 into here, and when I do that, I am going to get y is equal to 2, and x is equal to 1, so this would be 1 minus 4, that's going to give me negative 3. Then I need a unit vector that's in the direction of 3, negative 1. That unit vector is going to be 1 divided by the magnitude of this is the square root of 10, and then times 3 and negative 1. And so that's going to give me 3 divided by root 10 and negative 1 over root 10. And then when I take the dot product, I'm going to get 6 divided by root 10, and I'm going to get minus 3 times this is going to give me positive 3 over root 10, and my answer is 9 over root 10. Right, and then if we want to check that and compare that to the other two approximations that we got, we ended up with an approximation up here was 2.806, and the first approximation that we got was where is it? Was 2.53. Okay, so there's our two approximations, and if you put this in the calculator, that number ends up being equal to, I've got it written down somewhere here, is 2.846. Okay, so 2.846 is the actual answer, and you can kind of see that these two approximations weren't too bad, but this one was better, and we said that earlier. and the actual value is 9 divided by the square root of 10. All right, so what that tells me is that as I move in the direction of 3, negative 1, I'm going to be going uphill at this rate. Okay? All right, so I got a couple more examples that I want to do that are on the second page of this. But first of all, let's put down here the directional derivative. F in the direction of u at the point AB is equal to the gradient of f at the point AB and then dotted with a unit vector that's in the direction that I want to travel. All right, so let's take a look at this example. Find the directional derivative of this function at the point 1, 2 in the direction of 3, 4. All right, so to find this directional derivative at the point 1, 2, I need the gradient. The gradient of this function is the partial derivatives. The derivative of this with respect to x would be 2y minus 2x, and the derivative with respect to y would be just 2x. Then I need to find the gradient at this point 1, 2. So if I plug in y is equal to 2 and x is equal to 1, the first component is going to be 4 minus 2 is 2. And the second component is going to be 2 times 1, which is also 2. Then I'm going to dot that with a unit vector in this direction. So the unit vector then would be 1 over the magnitude, which is 5, and then times 3, 4. All right, so this is going to be 3/5 and 4/5. Right, and remember, the dot product is going to give me a scalar, so multiply 2 times 3/5 is going to give me 6/5, plus 2 times 4/5 is going to give me 8/5. And when I add those up, I'm going to get 14/5. 14/5 is the answer to that question. Okay. Moving on to the next one. This question is going to be very much like this one, but a little bit messier. All right, so find the directional derivative of this function at this point in the direction of this vector. All right, so again, we're going to have f in the direction of u at the point negative 1, 4. So we're going to need, first of all, the gradient of f. All right, so the derivative of this function with respect to x is going to be 2x square root of y, and the derivative of this function with respect to with respect to y is going to be x squared times the derivative of square root of y, which we've done this a couple of times, is 1/2 or 1 over 2 square root of y, derivative with respect to y. And then what we want to do is find out what is that gradient at this point. And so I'm going to plug in negative 1 and 4. So we'll get 2 times negative 1 is negative 2, times the square root of 4 is 2. Negative 2 times 2 is negative 4. And then if I plug in negative 1 and 4 here, we're going to get 1 in the numerator and 4 in the denominator, and that one will be positive 1/4. Right, and then we need to dot this, and it's important that this is a unit vector. Okay, so a unit vector in the direction of 1, negative 1 would be 1 divided by the magnitude would be the square root of 2 times 1 and negative 1. So this will be 1 over root 2 and negative 1 over root 2. And we'll get negative 4 over the square root of 2. And then multiplying these two together, I'm going to get minus 1 over 4 root 2. Right, and then if you want to combine those, get a common denominator of 4 root 2. This needs to get multiplied by 4, so negative 16 minus 1 over 4 root 2. And your answer is going to be negative 17 over 4 square root of 2. And if it bothers you to have a square root of 2 in the bottom, then rationalize the denominator, but this is okay for an answer. Okay, so 2 examples there, very typical of the kinds of things you're going to be expected to do on homework and quizzes. All right, so next one is find the rate of change of this function as you move from this point towards this point. All right, so this one's worded a little bit different, but rate of change just means find the directional derivative. All right, and we're going to start at the point 1, 2, so we want to know what is the directional derivative at 1, 2. Okay, so we're going to need the gradient of this. The gradient of f is going to be a vector whose components are 2x and negative 2y. We're going to find that gradient at the point 1, 2. So put 1 in for the x and you're going to get 2. Put 2 in for the y and you'll have negative 4. And then I need to take these 2 points and find a unit vector that is in the direction of the displacement. All right, so let's first of all, let's think about this as a displacement vector. So we're going from 1, 2, 2, 3, 1. So x is going to increase by 2, and y is going to decrease by 1. And so we get that that's the direction, but then we want this to be a unit vector. So 1 divided by the magnitude is square root of 5, okay, times 2, negative 1. And so this vector gives me 2 over root 5 and negative 1 over root 5. Taking the dot product, we'll have 4 over root 5 and then plus 4 over root 5. And my answer is 8 over the square root of 5. This is the rate of change in that direction. Okay, so to find the directional derivative, this is just a nice formula that you're just going to take the dot product of the gradient with a unit vector that is in the direction that you're trying to travel. All right, so with this then, we're going to be able to find the directional derivative in any direction that I want. We're not just restricted to going in the direction of x or the direction of y or the direction of the gradient and so forth. We can pick any direction that we want and travel in that direction. Okay, so that should get you through the rest of 14.4. This is about the directional derivative. So on your assignment sheet, you should be finishing up the rest of 14.4 for the weekend. And then also don't forget to finish your take-home quiz and make sure that you get that turned in on Monday. Okay, I will have some access to email, so if you got some questions, feel free to shoot me an email and give me at least a couple of hours to try to respond to it. But otherwise, have a great weekend, and I will see you Monday morning.